Hey guys, Francis here. In this video, we are going to learn about what is ICP and how does it work. ICP stands for Inductively Coupled Plasma. So the first question we should be asking is, what is plasma? A plasma is a conducting gaseous mixture containing a significant concentration of ions and electrons. Argon plasma is commonly used in ICP, where the principal conducting species are argon ion and electrons. So how do we generate argon plasma in ICP? Well, let's take a closer look at the instrumentation. This diagram here shows a typical setup of an ICP instrument, which consists of a sample introduction system and a plasma torch. First, let's take a look at the sample introduction system. In ICP, samples are introduced in a steady and continuous stream while an autosampler. The autosampler we will be using in this experiment can accommodate up to 60 samples at a time. A nebulizer then converts the liquid sample into an aerosol, which is a fine spray of droplets or mist. Then we have a spray chamber, which serves as a droplet-sized filter, where the larger droplets will be removed and drained, while the smaller droplets will be carried into the plasma torch. The ICP torch is made of 3 concentric quartz tubes, which argon gas flows through. The sample aerosol is introduced while the central tube. The tangential argon plasma support flow helps cool the inner walls of the central tube. The top of the outer tube is surrounded by a water-cooled induction coil, which is powered by a radio frequency generator. This will generate a fluctuating magnetic field. The ionization of the flowing argon is initiated by a spark from a Tesla coil. When the resulting ions and electrons flow through this region, they interact with the fluctuating magnetic field. This interaction causes the ions and the electrons within the coil to flow in a closed annular paths as shown here. The resistance of the ions and electrons to this flow of charge causes ohmic heating of the plasma. So this is how ICP works. Typically, modern ICP instruments offer 2 different viewing geometries for the measurements of atomic emission: the axial view and the radial view. The axial view offers a lower detection limit, while the radial view has a better stability and higher precision. So which one shall we use? In this experiment, we'll be using the axial viewing geometry, since we are interested in trace analysis of heavy metals in water sample. A lower detection limit may be more suitable for our case. If we are dealing with sample with higher TDS concentration, a radial viewing geometry may be selected. By the way, the plasma generated is quite beautiful. Feel free to take a picture of the plasma in the lab and post it in your Instagram. Finally, we have a simultaneous spectrometer that uses polychromator to isolate several wavelengths simultaneously. CCD detector is commonly used to capture all emission wavelengths. Now that we have learned how ICP and AES work, in the final part of this e-lecture series, we will discuss the experimental design in details. So see you in the next video. Bye!